Hello class. Today we are going to learn about quadratic functions. Now I promised that we would get to this eventually and we're finally here. This is Unit 8. The whole unit is centered around quadratic functions. What is a quadratic function? How do we evaluate them? What do they look like on a graph? And more or less their graphing features. There's certain features of these graphs that tell us a lot about a problem, and generally these are all real world problems. Let's start with the question though, what is a quadratic function? Well, how about I draw you a picture, because you all know I love to draw. Now, a quadratic function represents a real life situation. I'm going to draw you two scenarios, okay? Scenario A, Mr. Novotny climbs to the top of the Empire State Building. And he goes to the top level right on the roof and he says, I'm going to drop a rock right off the top of the building. And I have my rock in my hand and the rock goes all the way down and hits the ground. Now this line that I've just drawn, I'll outline it in blue, looks like a curved line. And believe it or not, it's governed by the laws of gravity. This line does not accelerate at a constant rate. It actually, or doesn't move at a constant rate. It accelerates. It accelerates at a constant rate. It's accelerating and getting faster as it's falling. And it's also moving away from this building because I've kind of tossed the rock out, right? So I've tossed it out and it's gained momentum traveling horizontally and then actually loses that horizontal momentum but gains momentum going in the vertical direction. This is a parabolic curve. Now, a parabolic curve or a parabola is another fancy name for a quadratic function. Okay, now let's say this function extended in the negative direction. It might look a little like that. And there's our typical U-shaped curve of a quadratic function. They're all U-shaped. And they're either upside down U's or right side up U's. So they're either smiling at you or frowning at you. Now, a quadratic function actually is always of the form f of x, or any letter of x, is equal to ax squared plus bx plus c, where a is always greater than 0. It could also be less than 0, meaning positive integers or numbers or negative numbers. It can never equal 0, because if it equaled 0, well, too bad. 0 times x squared would cancel out our x squared term. And the whole bearing of a quadratic is that it has an x squared term in its function. Now, a couple things you need to know. An upside down U, the value will always be less than 0, strictly less than. And the value of a for a regular U-shaped curve, looks like it's smiling at you, will always be greater than 0. So perhaps we could call my first curve of me dropping it off the building f of x equals the most basic of all quadratic functions, negative x squared. And the right side up u might look like f of x equals the most basic, just x squared. And if you typed both of them in your calculators, they would actually, I'm going to draw this for you, cross the coordinate plane at 0, 0, the origin. And perhaps I'll just adjust my curve in the slightest to represent that. Let's pretend that 0, 0 is right about there. And I'll just make a line down from my y-axis, a line across my x-axis. And now we're starting to resemble something that we find on a graph. Now, there's a couple of features we also want to keep in mind or bear in mind when we graph these functions. Every one of these quadratic functions has a minimum or a maximum value. It has a low point or a high point in the graph. Now, if it's a U-shaped, a positive quadratic function, if you will, it'll have what we call a minimum. All right, and it'll actually be the lowest point. And it's always in the y direction. So we're really looking for my y value of my lowest point here. Now in this case, my lowest point happens to be 0 on the y-axis. And in my other example, okay, and I'll just wound up making this into a little bit of a coordinate plane here. Looks like my minimum function, my maximum of this function is also at 0, 0. And it's the highest point, or the highest y value on my graph. Okay. Now there's other features that we will have to talk about, and I'm going to save them for when we get into the notes. But they'll include domain, range. We'll also talk about a function increasing and decreasing. And we'll also have to evaluate the functions based on certain values of x or inputs where we should be able to find certain outputs or y values of those graphs. Okay? All right. The last one that I'll just talk about here quick is, I'll draw you another picture. You ever hear about the cannonball problem? Right, so let's say there's a cannonball and boop, you get shot out of a cannon and it runs and it flies through the air, then it hits its maximum point and then falls back down to the ground. Okay, that happens to be a typical quadratic function problem. Now, if we're looking at this, we're given an x and a y axis. And the last point I want to make is that a lot of the time, we really need to know our initial value on the y-axis. Just as if we were graphing a linear function, where we find our slope-intercept form and our y-intercept is where we begin our graph, we can do the same thing with a quadratic function. And in its simplest form of a quadratic function, ax squared plus bx plus c, your c is always your initial value. It's your starting value on your graph, your y-intercept. And it can be very useful when you actually have to graph something because you always, for the most part, know where to start your graph. And I think for now that's enough. This is a good warm-up. All right, so I'll attach this video to the notes that I'll post as well. And I hope you guys can try to follow along with some of these new concepts. Again, we're on quadratic functions. This is the first lesson, lesson 1 in our new packet, and that's it. All right. Talk to you guys soon.